Today we are going to discuss in-situ stress and the capillarity, the two topics. First, looking at in-situ stress. Well, if you just look at the stresses or the stress in a soil mass, you can consider those stresses under two headings: geostatic stress and the stresses due to external loads. To have a clear perception, you can see this example that this is the ground surface. Groundwater table is present at this particular level, and a house is present over here. So if we just consider an element of soil, so you can see that here on this element we are having the geostatic stress, that is sigma V, and we are having delta PV, that is the added stress due to the weight of the house. So whenever we consider the geostatic stress, you will have to consider that one in terms of total stress or the effective stress. And you know, effective stress is equal to total stress minus pore water pressure. The principal source of soil stress is caused by the weight of the soil, adjusted usually by the pore water pressure above the point in the soil under examination. Additional stresses can and are induced by load from the soil surface, such as footings, deep foundations, embankments, and other weight-bearing structures. So when we consider the geostatic and hydrostatic stresses, so you will have to deal with the total stress, pore water pressure, effective stress and overburden pressure, upward seepage stresses if there is seepage, combined stresses. And when we consider the external load stresses, so you will have to employ the elastic method. Under that you can consider the Boussinesq stresses, Westergaard stresses, or Newmark method, or you can consider the empirical method 2:1 ratio. Well, this slide is very important. When a load is applied to soil, it is carried by the water in the pores as well as the solid grains. The increase in pressure within the pore water causes drainage, flow out of the soil, and the load is transferred to the solid grains. The rate of drainage depends on the permeability of the soil. The strength and compressibility of the soil depend on the stresses within the solid granular fabric. These are called effective stresses. Well, if you just look at the pore water pressure, pressure of water within the pores or voids of the soil, it can be caused by hydrostatic pressure, either direct from above or from down flow of water, capillary action, seepage, pressure from applied loads compressing trapped water. Water has a buoyant effect on soils under the water table. For hydrostatic conditions, this includes all soils under the water table. The buoyant effect of the water equals the weight of the water the soil displaces. So simply we are considering the Archimedes principle over here. This reduces the effective unit weight of soil for the purposes of calculating effective stress. Now the effective stress. The total stress minus the pore water pressure, that is the effective stress. So sigma sub effective, that is if you are having the number of layers, so summation of this H1 multiplied by gamma T1 minus pore water pressure. Equation only considers the load of the soil itself. One of the most important concepts in the soil mechanics. That is also called as the effective stress principle. As depth increases, soil stress generally increases because of increasing H. Varying unit weight will vary effective stress. Above water table, pore water pressure is generally not considered except for capillary condition. Now look at the stress diagram. We are having the three different layers over here. So you can see that you are having this type of pattern. And here you can say this is the inflection point. This is another inflection point. Inflection points due to changes in unit weight, water table, etc. Some useful information is given over here. The stress diagram is a useful tool to visualize the increase of effective stress or overburden pressure as a function of depth and to clearly see the effect of the pore water pressure. It can also be used in some cases to illustrate the changes that take place with applied loads and other conditions. So total stress in multi-layered soil. So in this model you can see there are three different layers and we are considering this element which is situated at a depth of Z from the ground surface. The total stress at depth Z is the sum of the weights of soil in each layer thickness above. Vertical total stress at depth Z, we can write this equation like that. Sigma sub V is gamma 1 d1 plus gamma 2 d2 plus gamma 3 into z2 z minus d1 minus d2. So we are just considering this one for the third layer. So we are considering the different depths d1, d2 and this one. So gamma 1, gamma 2, gamma 3 are the unit weights of the soil layers 1, 2, 3 respectively. Now look at this example. You are being asked to plot the variation of total and effective vertical stresses and pore water pressure with depth for the soil profile shown below. So look at that, we are having the gravelly sand topmost layer, then the sand and the sandy gravel over here, and the groundwater table is present over here. Now to plot the stress diagram, you will have to carry out this exercise. Within a soil layer, the unit weight is constant and therefore the stresses vary linearly. Therefore, it is adequate if we compute the values at the layer interfaces and water table location and join them by straight line. So this is the basic theme of the stress diagram. So at the ground level, sigma V is equal to 0, effective stress is 0 because the pore water pressure is also 0. At 4 meter depth, the total stress, total vertical stress is 4 times 17.8 and it is 71.2 kPa, and the pore water pressure again 0. So effective stress is total stress minus pore water pressure is equal to this. So here at 6 meter depth, first the total stress, then the pore water pressure, and then the effective stress. Then at 10 meter depth again, first the total stress sigma V, then the pore water pressure, and then the effective stress. And then at 15-meter depth, similarly, we have determined the sigma V, the total vertical stress, then the pore water pressure U, and the effective stress at that particular level. Now, when you are having all these values with U, we can plot the stress, or you can say the pressure diagram like that. So this one is the pore water pressure, this one the effective stress, and this is the total stress diagram. So stress versus depth plots. Now here another example, the soil profile, and by carrying out that analysis you can draw the total stress diagram, the pore water pressure diagram, and the effective stress diagram like that. Similarly, you can see the example number 3. This is the profile, and again you can see that this is the total stress diagram, or the total stress distribution along the depth. This is the pore water pressure distribution, and this is the effective stress diagram for this particular case. Okay, now we have reached here on this slide, stresses in saturated soils without seepage. So seepage is not being taken place in this case. So you can see in this model we are having this soil, and above that soil you can see that the water is present, and we have connected the piezometric tubes at this level, at this, and at this. So we are interested in at point A, point B, and point C. So you can see this thing that this C point is located at a depth of Z from A. H1 is the depth of the water that is present above the point A, and you can see that the total thickness of the soil, that is H2, capital H2 over here. So you can see that we are having the same levels in the piezometric tube. The reason is that there is no flow, there is no seepage at all. So at A, the total stress is gamma W into H1, obviously. Pore water pressure, again gamma WH1 because of the water, because total stress is either because of the soil or water, whatever present above that particular point. And the pore water pressure is purely from water, and then effective stress, total stress minus pore water pressure is equal to 0. Then similarly at point B you can see that the total stress is gamma W into H1 plus gamma W H2. Very simple. And then pore water pressure, this would be again, it will be calculated by gamma W multiplied by H1 plus H2, or gamma W H1 plus gamma W H2, and thus the effective stress, this becomes equal to that H2 multiplied by gamma saturated minus gamma W, and that is equal to H2 times gamma dash, and this is the submerged unit weight of the soil. Similarly at point C, which is which is this one, the total stress sigma C is equal to gamma WH1 plus gamma saturated into Z. Pore water pressure, that is because of water, so gamma W multiplied by H1 plus Z. Then the effective stress, that is equal to this one, gamma W saturated minus gamma W multiplied by Z, or replacing it by gamma dash or gamma submerged, so Z times gamma dash. So if you just look at the variations of the total stress pore water pressure and effective stress respectively with depth for a soil layer without seepage. So you are having this one, this is the total stress distribution, this is the pore water pressure distribution, and this is the effective stress distribution along the depth. Okay, there is one important point which is mentioned in the beginning of this particular slide, because now in the following slides we are going to discuss the cases of seepage. First we will consider the upward seepage case and then the downward seepage. If water is seeping, the effective stress at any point in a soil mass will differ from that in the static case. Static case when there is no seepage, that's the case that we have discussed in the previous slides. So I will repeat, if water is seeping, the effective stress at any point in a soil mass will differ from that in the static case. It will increase or decrease depending on the direction of seepage. So stresses in saturated soils with upward seepage, same model is there, but we are having the upward seepage. So look at that. This is the way with which we can show the upward seepage. The seepage is being taken place in the upward direction. And look at that. We are having the maximum level in this piezometric tube, which is connected to this level where the point B is present. Then this level that is at point C, and this one is corresponding to point A. Why there is drop in the level? Because there is head loss in the direction of flow. So the things which you can see over here, H2 is the thickness of the total soil, this H1 is the thickness of water which is present above that soil, and you can see one important thing which is there, this one, H dash over Z is equal to H over capital H2. This is basically the hydraulic gradient, head loss per unit length. So we are having this small h, this one, the difference between this level and this head loss is meant for this entire length or the thickness, that is H2. So small h over H2, this is the hydraulic gradient. If we just consider the flow from point C to A, so what is the length of flow in that case? That is Z. And what is the head loss from C to A? You can see that this is a level of piezometer tube corresponding to point C, and this is corresponding to point A, and let's say this one is H dash. So you can say H dash over Z, that is the hydraulic gradient. This is equal to H over H2, and from that you can get that H dash is equal to small h over capital H2 multiplied by Z. So that's why here it is mentioned, this one, the hydraulic gradient, that is equal to small h over H2 multiplied by Z. Okay, now at point A, total stress gamma WH1, that's fine, pore water pressure gamma WH1, so effective stress is equal to 0 as we had in the previous case. Now look at point B. Total stress at B is gamma WH1 plus gamma saturated into H2. So this is the total stress. Pore water pressure, this is gamma WH1 plus gamma WH2 plus gamma WH. So this is basically the additional thing that we have considered over here because of upward seepage. So keep this thing in the mind that when you are having the upward seepage, we will be using the positive sign and we will be considering gamma WH, and that is because of the seepage. So effective stress, this would be total stress minus pore water pressure, and after simplification you can see that H2 into gamma buoyant or gamma submerged minus gamma WH. So that is the additional thing that you are having if you just compare this case to the case when there was no seepage. Now try to extend this concept for the point C. The total stress is gamma WH1 plus gamma saturated into Z. Pore water pressure, here again you can see gamma WH1 plus gamma WZ, and this is the additional thing that we are considering with a positive sign because the seepage is in the upward direction. So the seepage is the upward direction, the positive sign will be used over here. And what is this? This is the hydraulic gradient, this one, and this is meant for the flow which is being taken place from point C to point A. So in this way, the effective stress, that is the total stress minus pore water pressure, so after simplification, ultimately, you are getting this thing. So Z times gamma dash minus I multiplied by Z gamma W. So I is the hydraulic gradient, that is H over capital H2. Okay. So you can see that we are having this thing additional with a negative sign over here. So what does this mean? What's the effect on the effective stress when the seepage is in the upward direction? Variation of the total stress, pore water pressure and effective stress respectively with depth for a soil layer with upward seepage, you would find over here. This is the total stress distribution, pore water pressure, and this is the effective stress distribution. Note that H over capital H2 is the hydraulic gradient, small I, caused by the flow, and therefore sigma dash, that is equal to Z times gamma dash minus Iz gamma W. If the rate of seepage and thereby the hydraulic gradient gradually are increased, a limiting condition will be reached at which sigma dash is 0. Effective stress becomes equal to 0. This is very important point. I will repeat, if the rate of seepage and thereby the hydraulic gradient gradually are increased, a limiting condition will be reached at which sigma dash, that is the effective stress, is 0. This one, 0. And you can see that in that case, when the effective stress has become equal to 0, we have replaced this hydraulic gradient by a critical hydraulic gradient. So where I subcritical, that is the critical hydraulic gradient corresponding to 0 effective stress, and from this you can get this one, that gamma dash over gamma W, this is equal to the critical hydraulic gradient. So keeping this thing in the mind that this is the submerged or the buoyant unit weight, and gamma W is the unit weight of water. Under such a situation, soil stability is lost. This situation generally is referred to as boiling or quick condition. For most soils, the value of critical hydraulic gradient varies from 0.9 to 1.9 with an average of 1. So you can see that when you are having the seepage in the upward direction, effective stresses are going to decrease. Okay, now look at the case. Stresses in saturated soils with downward seepage. Now in this model, the same model, but we are having the downward seepage. Look at the direction of seepage. So you can see here Maximum level of water is over here because the seepage is being taken place from A to B. Then we are having the list level and the minimum level over here, that is corresponding to point B. So again you can see that the hydraulic gradient is small h, this one, this level and this level difference divided by total length of the soil, that is h2. But this one is the head loss that you are having when there is flow from, you can see that this one, this level and this level. So when there is flow from point A to C, you are having the head loss equal to H dash, this one. I will repeat this thing. This is H dash. So H dash divided by Z equal to H over capital H2, and from here you can see this is equal to this. So that's why it is written that H over capital H2 multiplied by Z. Now carry out this analysis. At A, total stress is H1 gamma W, pore water pressure is gamma WH1, so effective stress is 0 again. At B, total stress sigma B is equal to gamma WH1 plus gamma saturated H2. Pore water pressure, that is gamma WH1 plus gamma WH2 minus gamma W small h. So here, as the seepage is in the downward direction, the negative sign will be used, and you can see that gamma WH is there, so you can write it like that. So the effective stress, that is the total stress minus pore water pressure, it is coming equal to that, and this is basically the submerged or buoyant unit weight, gamma saturated minus gamma W. Now extending this concept for point C, total stress sigma C, that is equal to gamma WH1 plus gamma WZ, and then the pore water pressure, that is gamma WH1 plus gamma WZ minus H over capital H2 multiplied by Z into gamma W. So that is the additional thing with the negative sign, and that is because of the seepage in the downward direction. So H over capital H2, that is the hydraulic gradient, so you can replace it by small I and you can write it like that, and thus the effective stress ultimately equal to this gamma submerged multiplied by Z plus IZ gamma W. Now on this particular slide you can see the stresses in saturated soils with downward seepage graphically. So this is, you can say, the variation of the total stress, here the variation of the pore water pressure, and the variation the effective stress. So if you just look at the previous slide again, with the downward seepage, effective stresses are going to increase. Okay, now look at the seepage force over here. You can see that this is the soil that we are considering over here. The volume of the soil is Z multiplied by area of the cross section of this soil. So the force that is there, that is gamma submerged multiplied by ZA. Now look at this. Well, this is the case when you are having no seepage. And when you are having the seepage in the upward direction and in the downward direction, so look at that. This is B figure that is meant for the upward seepage. So you can see here, this is the soil, volume of the soil is ZA, and the total force that you are having, that is equal to Z gamma submerged multiplied by A, and this is the seepage force which is acting in the upward direction, that is IZ gamma W A. Area is being multiplied just to convert the stress into the force, and you can see that if you just add these two things, you are getting this one, and you can see that the negative sign is there. So what is happening to the effective force that you are having? There is decrease in the effective force. And if you just look at this one, the downward seepage case, so here you are having gamma submerged into Z into A, this one, and the seepage in the downward direction, so you can see the seepage force is IZ gamma WA, and if you just add them together, so this is the effective force that you are having over here, and you can see that there is increase in the magnitude because you can see that there is plus sign with here. Seepage force per unit volume. The volume of the soil contributing to the effective force equals Z multiplied by A. So the seepage force per unit volume of soil is IZ gamma WA divided by ZA, so it is I times gamma W. So this is the seepage force per unit volume. Now look at this one, this model, a sheet pile, and the water is seeping in this direction, in this way. Here in the downward direction and then here in the upward direction. So here it is written that effective stresses increase because of the downward seepage, and here in this case it is written effective stresses decrease because of the upward seepage. We have already discussed these things in the previous slides. Well, to understand this thing, one paragraph is provided. Seepage forces play a very important role in destabilizing geotechnical structures. For example, a cantilever retaining wall shown in the above figure depends on the depth of embankment for its stability. The retained soil left side of wall applies an outward lateral pressure to the wall, which is resisted by an inward lateral resistance from the soil on the right side of the wall. If a steady quantity of water is available on the left side of the wall, for example from a broken water pipe, then water will flow from the left side to the right side of the wall. The path followed by a particle of water is depicted by AB in the above figure. As water flows from A to B, head loss occurs. The seepage stresses on the left side of the wall are in the direction of the gravitational stresses. The effective stress increases and consequently an additional outward lateral force is applied on the left side of the wall. On the right side of the wall, the seepage stresses are upward and the effective stress decreases. The lateral resistance provided by the embankment is reduced. Seepage stresses in this problem play a double role: increase the lateral disturbing force and reduce the lateral resistance. So you can say that seepage stresses in this problem play a double role in reducing the stability of a geotechnical structure. Now we will discuss the topic of capillarity. Capillarity. Capillarity arises from a fluid property known as surface tension, which is a phenomenon that occurs at the interface between different materials. For soils, surface of water, mineral grains and air. Then you would find the definition of surface tension. It is caused by each portion of the liquid surface exerting tension due to molecular attraction on adjacent portions of the surface or on objects that are in contact with the liquid surface. Capillary rise. The phenomenon in which water rises above the groundwater table against the pull of gravity but is in contact with the water table as its source is referred to as capillary rise. Water is sucked up into the pores of the soil in this zone on account of the surface tension of water, are manifestation referred to as the capillary phenomenon. Capillary water system. So we are having the three zones, important zones: zone of capillary saturation, zone of partial saturation, zone of contact water. So just go through that. Zone of capillary saturation, that is the closest to the groundwater table. Then zone of partial saturation. Above the zone of saturation is the zone of capillary saturation, and above is the zone of partial capillary saturation. In this zone, water is connected through the smaller pores, but more of the larger pores are filled with air. So that's why the word partial saturation is being used. Zone of contact water. The water in this zone surrounds the points of contact between soil particles and also surround soil particle but is disconnected through pores. So I will repeat that the water in this zone surrounds the point of contact between soil particles and also surrounds soil particles but is disconnected through pores. So that is the zone of contact water. So you can see over here, this is the groundwater table. Saturated soil with phreatic water. Phreatic water means the water table. Above that, saturated with capillary water. Then you are having the partially saturated with capillary water, and then the partially saturated with percolating water only. Capillary rise. A rise in a liquid above the level of zero pressure due to a net upward force produced by the attraction of the water molecules to a solid surface. For example, glass, soil, for those cases where the adhesion of the liquid to the solid is greater than cohesion of the liquid to itself. So immersing a glass tube of small diameter into a vessel containing water, and the rise of water in the tube is the function of the diameter of the tube and the clearness of its inner surface. So this is the simple model that we are having a container which has been filled with the water, and a tube is inserted, small diameter tube, and you can see that there is rise of water in that. Same thing can be considered in the case of soil, because we are having the interconnected voids, and you can see here that the water has risen up to a certain height, and that is the capillary rise. It is reasonable to assume that pore spaces between soil particles of various diameter behaves in much the same manner as that of capillary tube. In soils, shapes of void spaces between solid particles are unlike those in capillary tubes. The voids are of irregular and varying shape and size and interconnected in all directions. Hence, accurate prediction of the height of capillary rise in soil is next to impossible. However, the features of capillary rise in tubes are applicable to soils as they facilitate an understanding of factors affecting capillarity. Now here you can see we are having the micropores and the mesopores. Micropore means the pores of small size, and mesopore means the size, intermediate opening size. Well, if you just look at that, water has risen up to a certain height above the surface of water. The tube containing water exhibits positive capillary rise, where the water adheres to the sides of the tube, causing the fluid to rise slightly, as you can see over here. Now, if you just look at this model, this is the force of surface tension per unit length, and F is the force which is acting in this direction, that is equal to this capital T naught into pi d into cos alpha, because this one is making an angle of alpha with the vertical, and U sub c, that is the pressure because of that force, that is F over A, and that is this divided by pi by 4 d square, and that is equal to this. For chemically clean glass tube, alpha can be taken as 0. Capillarity and soil water energy. Soil water exists in small spaces in soil as a film around soil particles. The small pores can act as capillaries. A capillary is a very thin tube in which a liquid can move against the force of gravity. Water is attracted to the glass tube by adhesion, so a thin film flows up the side of the tube while cohesion drags water. The liquid rises to the point where gravity balances the adhesive and cohesive forces. The narrower the tube, the higher the water column can rise. So if you just look at this, considering the algebraic sum of forces in the upward direction, that is F minus W, you can say. So F is equal to W. Algebraic sum of forces in vertical direction is equal to 0. So when you will put 0 over here, so obviously F is equal to W. The formula for F is capital T naught into pi d, because alpha is being considered as 0. So minus pi by 4 d square h, that is the volume of this much water, pi by 4 d square multiplied by h sub c, and multiplying it by gamma w, you are getting the weight of the column of this liquid. At equilibrium, h sub c is at a maximum, therefore solving for h max, you can write this formula, that h sub c max, that is 4 T naught over d over gamma w. So here you can see that smaller the diameter of the tube, more will be the rise. So if you just look at that, in the soil we are having the interconnected voids or the pores. Height of capillary rise is a function of diameter of capillary tube, and you can take this formula for the soils, that d10 over 5, where d10 is the effective size of the soil, or you can say the diameter corresponding to which 10% soil particles are finer. Surface tension. The greater attraction of water molecules for each other than the air above at liquid-air interfaces, primarily due to cohesion. Adhesion and surface tension together cause the phenomenon called capillarity. the movement of water up a wick made of hydrophilic solid materials. Capillary movement takes place in any direction. The height of capillary rise in a tube is directly proportional to the liquid surface tension and adhesion to the solid surface, but inversely proportional to the tube radius and the density of the liquid. Now from here you can see the formula for the capillary rise, and look at that. For as an approximation of soils, put T is equal to that value, kiloton per meter, surface tension force per unit length, gamma W this one, alpha 0, and take D equal to nearly equal to E times D10, where D10 is the effective size in millimeter. So when you will plug in these all values, so you are getting this formula 30 times E over D10. This estimate may be improved to allow for the effect of grading and grain shape characteristics such as irregularity and flakiness. So you can write this formula in a general term, that C over E over D10. A rough approximation to maximum height h sub c to which water can rise by capillarity in a given soil is this one, where C is the constant and its value is from 0.1 to 0.5 square centimeter, and it's a function of grain shape and the surface impurities. E is the void ratio, D10 is the effective size in centimeter if you are using this constant in this range in centimeter square. Capillary action holds soil water in small pores against the force of gravity. The smaller the pores, the greater the movement can be. So capillary rise in different soils you can see, and you can see that you are having capillary head or the capillary rise more with the decrease of size of the particles. Relationship between grain size of uniform quartz powder and height of capillary rise. So from this you can see that you are having the height of capillary rise maximum corresponding to this. So H sub C is greatest for the fine grained soils, but rate of rise is slow because of their low permeability. So you can see from this that although when the particle size is reducing, you are having more capillary rise, but one thing must be kept in mind, that the rate of rise is slow when the particle size is small because of low permeability. So from here you can see that from this study, maximum for silts and very fine sand size particles. So if you just consider this particular size range, so you can see that from this particle size to this, over here you are having the maximum rise. Coarse grained soils are only partially saturated even at elevations close to the water level, whereas fine grained soils may be saturated for a considerable distance above it. So look at that. This is the groundwater table level, and because of the suction or the capillary rise, you can see the negative pore water pressure is there, and the soil is fully saturated up to a certain height above the groundwater table. The same thing you can see over here, that this is the groundwater table and you are having the capillary rise and the negative pore water pressure because of the suction is there, and here you are having the capillary saturation. The same thing can be seen over here. If you are having the capillary rise and you are going to plot the total stress distribution, the pore water pressure distribution, and the effective stress, so you would be finding these distributions like that. So you can see that this is the groundwater table level. You are having the capillary rise, the negative pore water pressure is there, and then you can see that you are having zero pore water pressure like that. And here you can say that up to this part you are having the partially saturated soil. And this is the distribution for the effective stress. Angle of repose. Dry, unconsolidated grains will form a pile with the slope angle determined by the angle of repose. The angle of repose is the steepest angle at which a pile of unconsolidated grains remains stable and is controlled by the frictional contact between the grains. In general, for dry material, the angle of repose increases with increasing grain size, but usually lies between about 30 degrees and 37 degrees. So you can see here, dry sand is being dropped like this. You are having this pile of sand. So this angle is the angle of repose. So we are having the grain to grain frictional contact, and that's why you are having this shape of that sand. The role of water. Think about building a sand castle on the beach. If the sand is totally dry, it is impossible to build a pile of sand with a steep face like a castle wall. If the sand is somewhat wet, however, one can build a vertical wall. If the sand is too wet, then it flows like a fluid and cannot remain in position as a wall. Slightly wet unconsolidated materials exhibit a very high angle of repose because surface tension between the water and the solid grains tends to hold the grains in place. So you can see this thing, solid particles, surface tension of film, thin film of water holds grains together. So because of that thin film of water, surface tension of thin film of water holds grain together, and you could be able to make the sand castle like that. When the material becomes saturated with water, the angle of repose is reduced to a small values and the material tends to flow like a fluid. This is because the water gets between the grains and eliminates grain to grain frictional contact. So look at that, because of increase of the water content, the water completely surrounds all grains and eliminates all grain to grain contact. Soils containing smectites or montmoronites expand when they become wet as water enters the crystal structure and increases the volume of the mineral. When such clays dry out, the loss of water causes the volume to decrease and the clays to shrink or compact. This process is referred to as hydrocompaction. So this is the unexpanded clay, and look at that, water has entered and there is an increase in the volume overall. Physical examples of capillarity phenomena. Well, if you just look at that, this is the groundwater table. Here in this part we are having the capillary zone. The water has risen up to a certain height like that because of the suction, and here absence of capillary water. Confining pressure results from the columns of water hanging on the different menisci at the surface of the beach. So this is basically the example we have got from the beach side. Relative density is more or less same. Only change is the presence of capillary moisture or its absence. When sea water breaks, capillary menisci gets washed off and temporarily induced shear strength is lost. So if you just look at that, we are having the absence of capillary pressure. So up to this we are having the poor strength. But here we are having good strength because of that capillary action, the capillary zone is there, and you are having the temporary induced shear strength in this zone. And then again we are having the poor strength for this soil which is just present underwater. So physical examples of capillarity phenomena: two soil grains held together by a capillary film. Look at that. Two soil particles, capillary water in wedge formed by the soil particles, but you are having the contact between the particles. So in this way, you will be having the bulking structure in sand is due to capillary action. Strength gain in a granular soil due to partial saturation and surface tension is termed as apparent cohesion. So you would be having the honeycomb structure in a granular soil like that. Now at the end of the lecture you would find this example. For the soil profile shown in the figure, draw total stress, pore water pressure and effective stress diagram. The soil in capillary zone is assumed to be saturated. So considering this one, this profile, so you can solve that problem yourself. In fact, this is the solved example that the solution you would find over here. So statement of the problem: a 3.5 meter thick silt layer underlain by a 3 meter thick clay layer is shown in the figure. Calculate the total stress, pore water pressure and effective stress at points A, B, C, D and E. The water table is located 2.5 meter below the ground surface. The capillary rise in the silt layer is 1.5 meter. Assume that, well, this last sentence is very important. Assume that the silt layer has a degree of saturation S sub bar equal to 60% in the zone of capillary rise. So in this interesting example, in the capillary zone of capillary rise, we are not having 100% saturation. We are having the degree of saturation equal to 60%. So what to do in this case? Normally we have 100% saturation, but here, at least in this example, we are having 60% degree of saturation. So look at this one. This is the last slide for today's lecture. So in fact, this is the silt layer and the groundwater table is lying over here. So we are having the rise, capillary rise, but the degree of saturation is not 100%. So what to do in that case? So that is the new thing, the new concept, the concept given by Halvany in 2007. Well, you can draw the total stress diagram very easily. Considering the partially saturated soil over here, and then you are considering the pore water pressure distribution diagram. The only difference would be for this part. here this will be 1.5, that is the thickness of the silt layer, multiplied by gamma water. If degree of saturation of this soil is 100%, then you don't need to use this one over here. It will be equal to 1. So you can say it is 1 into 1.5 into 9.81 if this silt is fully saturated. But as this is not fully saturated, degree of saturation is 60%, so in that case you will have to use 0.6, or you can say 60 over 100. And the negative sign is there because you are having the capillary rise because of suction, so the negative sign is to be used. So here you can say minus 8.82. So that's the only difference. The rest of the things are same. You can draw the remaining part of the pore water pressure distribution diagram and then the effective stress diagram, keeping this thing in the mind that the effective stress is equal to total stress minus pore water pressure. So that's all about the in situ stresses and the capillarity. Thank you.